what exactly the bit, nibble, byte, word, double, all those things, and also we define the stack. We define the stack. So in this class, we are going to elaborate the explanation related to the stack. After that, we are going to relate the stack operation. How exactly means how exactly the stack is going to be utilized by the microprocessor during the execution of any kind of program like C program or your assembly language program, whatever it is. So how exactly that stack area is going to be used by the microprocessor, which we are going to study in this session. Okay, now so let us take the transition. So I will go to my slides. I will go to the slides. I think it is recording, right? So now let us define what exactly the stack. So stack is nothing but a part of the RAM memory. A part of the RAM memory is called as a stack. A part of the RAM memory is used as a stack. Okay. And what is the main use of the stack memory? It is used for holding the data and the addresses during the execution of the program temporarily. Holding the data and addresses during the execution of the program temporarily. So that is what the stack. Now, let us suppose if you want to perform reading operation on the stack memory and writing operation on the stack memory, means if you want to read the data from the stack or if you want to write the data onto the top of the stack, how exactly it is going to be done is a question. So in order to perform the read write operations with respect to the stack, in order to perform the read write operation with respect to the stack, we are having two instructions called as a one is a push, another one is a pop. One is a push, another one is a pop. Okay, what exactly the push operation? Let us define the push. So push is nothing but it is used for writing the data onto the top of the stack. It is used for writing the data onto the top of the stack. Okay. So how exactly the microprocessor is writing the data onto the top of the stack using the push instruction is a question. So for that we are having the steps. So means steps followed by the microprocessor to write the data, to push the data onto the top of the stack is a step 1 is first it decrements the SP register content by 1. Now, so before following these steps, let me define one thing which I thought I included the point, but which is not there. So let me define what exactly the SP register. SP register is nothing but the stack pointer register which points the address of the top of the stack. Stack pointer register which points the address of the top of the stack. Address of the top of the stack means what is the last memory location which is used in the stack area, that is going to be shown by the stack pointer. That is going to be shown by the stack pointer. Means stack pointer is holding the address of the last instruction which is utilized by the microprocessor in the stack area. Which is utilized by the microprocessor in the stack area. We are having the BP also, which is nothing but the base pointer. I'll come to that point. Base pointer is nothing but which shows the what is that starting address of the stack for a particular program. It is not the base which you have seen in the segment case. Okay, now. So it is going to be the different one. So in order to show the base address of your stack segment, we are having the SS register. But here BP is nothing but the base pointer which is showing the starting address of the stack for a particular program. I'll define that one, no problem at all. So just now SP is nothing but the stack pointer which shows the address of the top of the stack, which shows the address of the top of the stack. Okay, now. So address of the top of the stack means what is the last memory location which is utilized in the stack area, that is going to be shown by the stack pointer content. Okay, now, which is holding the address. Okay, so here the steps followed by the microprocessor to push the data means first it decrements the stack pointer register. First it decrements the stack pointer register content by 1. It decrements the stack pointer register content by 1. A stack pointer register content is nothing but the data which is available in the stack pointer. Actually, it is not the data, it is the address of the top of the stack. That particular address available in the stack pointer is going to be decremented by 1 or 2. That depends on whether you are writing the 8-bit information or you are writing the 16-bit information, 16-bit data or the 8-bit data onto the top of the stack. Whether you are writing the 8-bit data or 16-bit data onto the top of the stack. Depending on that, if it is an 8-bit data, stack pointer is decremented by 1. If it is a 16-bit data, stack pointer decremented by 2 in order to hold the 16-bit data. So after decrementing the SP register content by 1, microprocessor pushes the data onto the top of the stack. Means it is writing the data onto the top of the stack. For example, if you want to know that one, let me take one simple area. Assume that this is my stack area. This is my stack area. The red box is a stack area, and I am assuming that these are the memory locations which are there in the stack. So this is the first memory location. This is the second memory location. Means we are having the lots of memories, but I am just showing only the few instructions, a few memory locations. Okay. So assume that the top of the stack means this is the top of the stack. I am assuming the address of this particular top of the stack. Address of this particular top of the stack as a indicated by whom? SP. I am assuming this value is a let me redefine that. Let me take this SP. I'm going to take SP. I'm assuming that the starting address is going to be the means what is the last memory location. So I'm assuming that this is the last memory location which is utilized by the microprocessor in the stack area. So I'm assuming that address as a 0009H. I'm assuming that address as a 0009H. I think you are not able to see this one, right? You are not able to see this one. I hope you are able to see. Okay. So here we are having the still confusing. Okay. What I'll do is I'll come out from here and I'll go for this. Yeah, this one is the best option. So what I'm going to do is I'm going to take some memory locations by inserting some rows and columns. No, it is not the good one. Okay, so I'll go for one diagram, drawing one diagram over here. Assume that this is my stack area, and this is the starting address. This is the first memory location of my stack. Means we are having the vast size of the stack, but I'm just taking only I'm just considering only the few memory locations. Okay now. So assume that these are the memory locations, and we are having the lots over here, and the down also. From the down we are having the so many memory locations, so many memory locations. So here I'm assuming that this is the address, this is the last address, means extended to this one, means in the down. Let me take the red color to show that this area is already having the, this is a stack area which is already utilized, and I'm assuming that this is the top of the stack, this region is the top of the stack. So for that I'm taking one register. Which register is showing the top of the stack? SP register, and I'm assuming that SP register is showing the top of the stack. SP is equals to I'm assuming that this memory location, whatever the memory location we are having, I'm assuming that memory location address is a 0009H. So means this is the 0009H memory location. Okay. Now when the microprocessor wants to perform the writing operation, means it would like to write the 8-bit data onto the top of the stack. It would like to write the 8-bit data onto the top of the stack. Okay. So when it wants to write that 8-bit data onto the top of the stack, what it will do means, I'm assuming that that 8-bit data is nothing but I'm assuming this 8-bit data is a 63H. I would like to write the 63H. This is my 8-bit data. This 8-bit data I would like to write on the top of the stack. On the top of the stack. So as per the microprocessor, SP content by 1, which is nothing but what? Oh, I forgot to take this one as a 0009. Wait a minute. So it should be the 0009, right? SP register is equals to the 0009H, because it is a 16-bit number, 16-bit register. So I would like to store the 63H, which is a 8-bit number, 63H onto the top of the stack, So this is the last memory location. I am assuming that 0009H is a last memory location used by the microprocessor in the stack area. Last memory location used by the microprocessor in the stack area. Now, so as per this statement, first microprocessor decrementing the SP register by 1. So 63H is nothing but what? It is the 8-bit data. 8-bit data means 3 is the 4-bit number, 6 is also the 4-bit number. As I told you that when you are writing the hexadecimal format, each digit is a 4-bit number. Each digit is a 4-bit number in the binary combination. So 63H is nothing but it is a 8-bit number. So this 8-bit number should be pushed onto the top of the stack now. As I said, when you are trying to push the 8-bit number, the stack pointer decremented by 1. So decremented by 1 means first it decrements. Step 1, microprocessor decrements the SP register by 1. So means 0009H is going to become, what is that value? Let me take the red. So 0009H SP content, new value in the SP content is equals to the 0008H. 8H. Okay now. So 0008H, but if I'm doing like this, then definitely you can't see that value. Okay, so I'll take over here. Okay, SP value, as it is decremented by 1, SP new value becomes a 0008. I'm not writing the H, but it is the hexadecimal number only. So first it decrements the SP register content by 1. After that pushes the data onto the top of the stack. Now, which data you would like to write? 63H. Now the 63H is going to be written over here. Okay, now 63H is going to be stored over here, which is a 63, which is a 63H. So means first it decrements the stack pointer by 1. So previously I assumed that this entire region is already used by the microprocessor, and then now present top of the stack is a 0009H. When the stack pointer is pointing the top of the stack as a 0009H, I would like to write the next data, which is a 8-bit number 63H. At that time, microprocessor decrements the SP register content by 1. Means it is decrementing the SP by 1 means 0009H minus 1 is nothing but it is going to be the 8. It is going to be the 8. Okay. Now. So now this address is this is the address which is showing the top of the stack. And to this address, where the microprocessor is going to be write the 88-bit data, which is nothing but the 63H. So it is going to be the 63H. Now let us suppose microprocessor wants to write the what is that, 16-bit data. 16-bit data means 4-digit hexadecimal number. I'm assuming it as a 1234H. 1234H. If you take this one, 1 is a 4-bit number, 2 is also the 4-bit number, means each and every digit in the hexadecimal format is representing the 4-bit format. Now this one is what, ma? This is entire thing is a 16-bit number. This entire thing is a 16-bit number. Now we are interested to push the 16-bit data onto the top of the stack. Now at that time, microprocessor decrements the SP register content by 2. Microprocessor decrements the SP register content by 2. But initially it is going to be decrements the SP register content by 1. And after that, as it is a 16-bit number, 2 times the SP content is decremented by 1, Means in the first decrement operation, I'm going to take the red. In the first decrement operation, SP is decremented by 1. SP is going to be decremented by 1. So previously SP value what? 0008 na? Now the SP value is going to be the 0007. So which address? Oh, ఇది కొంచెం uncomfortable ఉంది. Wait a minute. So this address is representing this location. Okay now. Into this location, microprocessor is going to be raised the. So here we are having the 16-bit number na. As we know that in this 16-bit number, these 2 bits are indicating the higher order byte, because it is a group of 2 8-bit numbers. So this is the 12H is a higher order byte, 34H is a lower order byte. 34H is a lower order byte. So in the first decrement operation, here we are trying to write the 16-bit data. So when you are writing the 16-bit data, SP is decremented by 2. Decrement by 2 is going to be done in the 2 steps format. First it decrements SP by 1 and stores the higher order byte of your 16-bit number. Higher order byte of your 16-bit number means now this value is going to be let me take green only. So it is going to be the green. It is going to be the how much? It is going to be 12. 12 is going to be stored over here in this memory location in the 0007. 12 is going to be stored. So here the next decrement, 2 times it is going to be decrementing the SP by 1 na. Now the 2 times, second time the SP value is going to be how much? SP is going to be points the 0006, which is there in the SP register. So I'm just taking the right side because for my convenience, it is going to be the 0006 because we are trying to store the 16-bit data. We are trying to store the 16-bit data. Now it is pushing the on the 0006H memory location onto this memory location. It is pushing the lower order byte, which is nothing but the 34, which is nothing but the 34. Okay, now 34H is going to be written over here. It is going to be the 34. It is going to be the 34. If you want the simple one, I'll take the blue color only. I'll take the blue for 34H. 34H is data is going to be stored over here. 12H is data is there in the 7th memory location. 34H data is there in the 6th memory location. 6th memory location. Okay, now. So means when you are trying to store the 16-bit data onto the top of the stack, SP is decremented by 2 by decrementing the SP content twice. Means it is decremented by 1 only, but in order to store the 16-bit data, that decrement is going to be done twice. But if you want to store the 8-bit data, then the decrement is going to be done by only one time. Only one time. Now, if you see this one, see, in the first decrement operation, it is going to be the 7. Na? So, when in the first decrement operation, the higher order byte of the 16-bit number is going to be stored, and in the last memory location, that is nothing but 0006, last value is going to be the lower order value, which means what I mean to say that when you are taking the 16-bit data, higher order byte is going to be stored first and the lower order byte is going to be stored next. Okay, now higher order byte is going to be stored first, lower order byte is going to be stored next. So the lower order byte is going to be stored next. Now let me take this one because my time is not running. Let me see. Yeah, it is going to be the twice. Oops. Higher order byte is going to be stored first and lower order byte is going to be stored next. Na? So that's why the microprocessor is called as a little endians. Microprocessors are called as a little endians. Means in the 16-bit number, I'm just taking in short. So in the 16-bit case, so if I'm taking this is another area, this is another area. So previously we took it as a stack pointer by 7. Na? So I'm just taking it as a red and SP register content is equals to 007H, and let me take another one over here. SP register content, SP register is equals to the 006H. So what was the value we are interested to write? We are interested to write that 1234H, which is a 16-bit number. So out of 16-bit, this one is the higher order byte and this one is the lower order byte. We have defined that one. So in the 16-bit combination, most significant 8 bits are called as the higher order byte, least significant 8 bits are called as the lower order byte. And in this case, when you are trying to perform the writing the 16-bit number, first higher memory location means it is decremented. Previously it was the 8 na, so that is decremented by 1 means it is going to be the 7. So over here it is going to be written as, what was that, 12H. 12H is going to be written over here, and here 34H is going to be written. So if you see this one, so in the first case, means in the first decrement operation, higher order byte is going to be stored first onto the top of the stack. In the next decrement operation, lower order byte is going to be pushed onto the top of the stack, is going to be written onto the top of the stack. So which value is now available as the top of the stack? 34H, which is a lower byte. Means in short, in the, if you see this one, this is a least memory location, this is a means higher memory location, means the one address is more. So 7 is higher memory location, 6 is a lower memory location. In the higher memory location, higher byte is going to be stored. In the lower memory location, lower byte is going to be stored. Or I can say that when the microprocessor is trying to push the 16-bit data onto the top of the stack, first of all, it is going to be pushes the higher order byte onto the top of the stack, and the lower order byte is going to be the last. Means when you would like to store the 16-bit data, first it is pushing the higher order byte, after that it is pushing the lower order byte. So once it is done, the lower order byte, means the top of the stack is going to be the 34H. So as it is holding the lower order byte value on the top of the stack, the microprocessors are called as microprocessors because of this reason. Because of this reason, microprocessors are called as a little endians. Microprocessors are called as little endians. Why it is called as a little endians means when the microprocessor would like to push the data onto the top of the stack, in case of the 16-bit number, not only in case of the 16-bit number, it may be the 32-bit number, whatever it is, on the top of the stack. When it is trying to push the 16-bit number or the 32-bit number on the top of the stack, lower order byte is going to be pushed onto the top of the stack. So that's why the microprocessors are called as I'm just taking microprocessors, MPs. Microprocessors are called as little endians. Okay, little endians. Okay, little endians means the top of the stack is going to be the lower order byte when you are having the 16-bit number data or 32-bit number data, whatever it is. Okay, so it is going to be the little endians. It is going to be the little endians. Okay, so this is all about your pushing operation with respect to the stack. Means if you want to push the data onto the top of the stack, you are supposed to use the push instruction. When you are using the push instruction, microprocessor simply decrements the stack pointer value by 1 or 2 depending on the size of the data. If it is 8-bit data, it is going to be decrements the stack pointer value by 1 and pushes the data onto the top of the stack. Or if it is a 16-bit data, it is going to be decrements the stack pointer by 2 in twice format and pushes the data onto the top of the stack. When it is trying to push the 16-bit data onto the top of the stack, in the last memory means on the top, the little lower byte is going to be stored pushed onto the stack later, means on the top of the stack lower byte is going to be there. So that's why the microprocessors are called as also called as little endians. It is one of the competitive exam question. Okay, now so microprocessors are also called as pre-decrement operation because before pushing the data onto the top of the stack, as the SP is decremented by 1, so that's why push operations are also called as pre-decrement operation. Push operations are also called as pre-decrement operation. Now let us go for the pop. So it is going to be the reverse order. Okay, so pop is nothing but this instruction is used to read the data, to pop the data from the top of the stack. We are having the pop instruction. So in this case, the operation is going to be reverse. First, it reads the data from the top of the stack and stores the information into the first it reads the data from the top of the stack and stores the information. Sorry, it is not the storing the information actually. So okay, so first it pops the data from the top of the stack and it is going to be increments the stack pointer by 1. Okay, now so means if you are taking the stack area, so I'm just taking the stack area. So this is the first memory location, this is the next memory location, this is the next memory location. Let us suppose this is the top of the stack, this is the top of the stack. Then what the microprocessor is doing is microprocessor first reading the data from the top of the stack. Once you read the data from the top of the stack, this memory is not required. Okay, now because we already read the top of the stack register value. Now the top of the stack is going to be this one. So obviously we know that when you are taking the top of the stack, the least one is the top of the stack, right? Let me take the previous example. So I'm going to have, let us suppose I'm having the SP register is equals to the 0006, right? So once you done the reading operation, so this is the top of the stack. Now this is the top of the stack. I'm assuming that this value is going to be read into the destination. This value is going to be read into the destination. At that time, this SP is incremented by 1. SP is incremented by 1. Now the SP value is what, ma? Incremented by 1 means SP is pointing the 0007 memory location. Previously it was 0006. Now it is going to be the 0007. So that's why the pop instruction is also called as a post increment operation. Means first it reads the data from the top of the stack into the destination, and once you read the top of the stack value, no need to hold the address of the top of the stack. So we are interested to hold the address of the, now once you read the information from the top of the stack, now the top of the stack is going to be becoming the 7. So that's why it is incremented by 1. So after reading the data from the top of the stack, only the SP register content is incremented by 1. So that's why the pop instruction is also called as a post increment operation. Pop operation is also called as a post increment operation. So pop is nothing but simply to read the data in simple format, to read the data. That is nothing but the pop operation. Okay. So this is all about your stack which is going to be used in your microprocessor case, and it is one of the important short question. They may ask you that briefly explain about the push and pop instructions. Briefly explain about push and pop instruction, or briefly explain the stack operation in 8086 microprocessor. Then you are supposed to take the push as well as the pop instructions. Okay, now during the instruction set also we will come across this one. But as I raised the question with respect to the C language, so I just defined the push and pop instructions over here itself. Okay, now let us go for how could we relate whatever the push and pop instructions we have seen right over here. How could we relate this one to our C program is a question. To our C program is a question. Okay. So here what I'm doing is sorry. Yeah. Here I'm assuming that this is my main function and this is a sub-function, subprogram function 1, and this is another subprogram function 2. I'm assuming that in the function in the main function I'm calling the subprogram fun1. In fun1 again I'm calling the fun2. In fun2 I'm calling the fun2 now, and this is the definition of the fun2. This is the definition of the fun2. Now before going to have the in detail explanation, okay, I'll take a in short. So before going for in detail explanation, what I'll do is let us define what exactly the means, what is happening when you are using the declaration part. So we know that in any function body, when you are writing a function definition, in any function body, the first part of the function body is a variable declaration. In C language, in C++ it is going to be the different. Wherever you want, you can declare the variable just before using the variable for the first time. Okay, now just before using the variable for the first time, you can declare your variable in the C++ programming, but it is not the case in C language. So whatever the variables which you would like to use in your C program, all those variables should be declared in the first part of the definition of that particular C program. Okay, now so this is the declaration of the variables. I'm assuming that two variables are there, a, b, and in the function 1 also I'm declaring one variable which is a x. In the function 2 also I'm declaring another variable which is a y, which is going to be the y. Okay, so now the question is, when you are trying to execute this kind of program using the Turbo C compiler or any C compiler, when you are trying to execute this particular program, whenever you are declaring the variables and trying to run your program, at that time, without knowing to you, declaration part of the variable is nothing but C compiler is going to be request the microprocessor to allocate some memory area for your variables which are defined in the first program. That is in the main function. Means when you are running the program, first function which is going to be executed by the C compiler is main function. So main function, when you are trying to execute the main function, the first two variables means you are having the variable declaration. As you are having the variable declaration, immediately microprocessor is means this C compiler is requesting the microprocessor to define, to allocate two memory locations. Why I am taking the two memory location means the char is a 1 byte variable. Char data type is a 1 byte. I am not taking the what is that int and the float, because depending on the compiler size, the int size is going to be the 16-bit or the 32-bit. Float size is also going to be varying, so it may be the 32-bit. Okay, now so instead of avoiding the confusion, what I done is, in all the functions I took only the character type variable. I'm not taking any int value, I'm not taking any float value. To avoid the confusion, I just took the char type variable. It is only for a brief explanation. Okay, now so if you realize this concept, then realizing the rest of the thing is very, very easy. Okay, so as you are declaring the variables now, as you are executing the main function for the first time, you are asking the microprocessor to allocate some space for the A and B instructions. So how many bytes of data means carries nothing but 1 byte of data type. Okay now. So as you are declaring the two variables, then 2 bytes of memory is going to be allocated by the microprocessor during the execution of this program. How it is going to be done, the allocation, we will see that one. Okay now. So here you are declaring over here in the function 1. So what you are doing during the execution of this one, first declaration is over. When you are executing the fun, means you are calling the function 1 function, at that time the execution control is going to be diverted from this point to this point, because it is not executed the termination of the main function. It's simply diverting the execution control from here to the function 1. In the function 1 also, again you are having the declaration part. Means again you are asking the microprocessor, again the compiler is asking the microprocessor to allocate one more memory location. Yeah, let me tell you one important point, that from 8085 microprocessor onwards, before that we are having a different scenario. From 8085 microprocessor onwards, each memory location is able to hold the 8-bit information. Each memory location is able to hold the 8-bit information. Remember that point. Each memory location is able to hold the 8-bit information. Means if you want to store the 8-bit number, you require the one memory location. If you want to store the 16-bit number, you need the two memory locations. So if you want to store 8-bit number, you require the 1 memory location. If you want to store the 16-bit number, you require the 2 memory locations. If you want to store the 32-bit number, then you require the 4 memory locations. Okay, now 32-bit means equal to divide that one with the 8-bit, then it is going to be the 4 bytes. Okay, now 4 bytes means 4 memory locations. So from 8085 microprocessor onwards, memories are able to hold the, each memory location is able to hold the 8-bit information. If you want to store the 16-bit data, 2 memory locations are going to be utilized by the microprocessor. Okay, 2 memory locations are going to be utilized by the microprocessor. So here you are diverting the execution control from here to here, means again in the definition of the function 1, again you are defining the one more character type variable na. For that also microprocessor is allocating the one more memory location. Means here it is allocating the 2 memory location space for 2 variables on the stack area, and here only one variable na. So one memory location is going to be allocated by the microprocessor on the stack area. So again in the what we say, in the definition of the function 1, I am calling the function 2. In the function 2 also we have the one more variable, means one more character you are declared. So because of that, you are requesting the microprocessor to allocate one more memory location. Okay now. So means the declaration part of the variables in C language is nothing but using the C compiler, you are asking the microprocessor to allocate so and so number of memory locations for for the variables. How many variables you are declaring in your C program? Now the question comes that actually we are interested in concentrating on what? We are interested in concentrating on the open brace and the close brace. Okay, open brace and the close brace. What exactly the open brace and what exactly the close brace? Open brace is nothing but, the open brace is going to be shows that from where exactly the stack memory is going to be allocated for the main function. From where exactly the stack memory is going to be allocated for main function. So that starting point means that starting address of the stack for the main function, which is called as a base address. SS register is a stack segment register which is holding the base address of the entire segment. But for every function we require the stack area na? For every function we require the stack area na? Means for every function a fresh copy of the stack is there, which is available in the stack segment only, but for every function there is a fresh memory allocated for the stack. Okay, so here you, as when you are starting the open brace, then this particular open brace is going to be decides that what is the base of the stack which is allocated for your main function. So that is there in the BP. BP is nothing but the base pointer which points the address from where exactly the variables which are declared for the main function are going to be stored on the stack. Okay now. So another case is we are having the this is a another open brace now. So I'll come to the close brace later. Okay now. So this is the another open brace now. After storing these two variables onto the top of the stack, again you are calling them subprogram. Means for this particular subprogram also separate stack area is there. So from where exactly the stack which is allocated for the function one is going to be started, that is going to be represented by again by the BP register. Means for every subprogram we are having the stack area which is a continuous one only. But in order to differentiate that from where exactly the stack is allocated for the function one, from where exactly the stack is allocated for the main function, from where exactly the stack is allocated for the function 2, that is going to be shown by the BP register. That is going to be shown by the BP register. Now the question comes up, what is the use of the SP register? SP register is showing the top of the stack which is allocated for the main function. BP is showing the starting address of the stack allocated for the main function. In that particular stack area, what is the top of the memory location? Top memory location which is accessed by the main function. That is going to be indicated by the SP register. That is going to be indicated by the SP register. BP is indicating the starting memory, starting stack area for the so and so function. SP is indicating the how far we moved from that particular starting stack area for that particular function. That is going to be indicated by the SP, stack pointer. Okay, now let me tell you without confusion. Let me tell you one important point. Okay, now let me take one simple example. So assume that 000DH is a 000DH is a BP value. Actually, when you are trying to execute the C program, na, so which is nothing but our main function, all those things, which is nothing but our main function, all those things. Okay, now when you are trying to execute this program, before your program, there might be some other programs which are running inside the memory, na? Is it or not? In order to run my system, my laptop, obviously so many functions are working. So for all those functions, we require the stack area. For all those functions which are running inside the RAM, we require the stack area. Okay now. So here previously, assume that when I started executing my main function, just over here, when I started to execute my main function, let me write all these things. Okay, Control E, and yeah, when I would like to execute my main function. Okay now, when I would like to execute my main function, as I said, we require the two memory locations now. Assume that from where exactly the stack is going to be allocated for my main function. I am assuming that this is the memory location, means from here, from the 000DH onwards, or this is the starting address of my stack area assigned for the main function. Okay, now assigned for the main function. Now SP value is how much? SP value is the BP value is going to be the BP. So here BP and SP. If I take the AND operation and SP. Okay, now. So BP is filled with what? 000DH, because the starting address of stack area which is allocated for my main program, I am assuming it is a 000DH. So obviously same content is going to be stored inside the SP also, because from there onwards you are supposed to perform the push and pop operation. From there onwards you are supposed to perform the push and pop operation, means the SP register content. Okay, cool Baba. Okay, it is going to be the SP content. Now in the main function, what you are doing, you are trying to declare the two variables. You are declared the two variables, means you are asking the microprocessor to allocate the two memory locations. So open brace is nothing but a new base pointer is allocated. A new base value for this program is allocated by the microprocessor, that is going to be stored in the BP register. Same value is going to be there in the SP register initially. So as we are expecting the two values now, so it is means you are allocating means you are asking the microprocessor to allocate the two memory locations. You are asking the microprocessor to allocate the two memory locations means you are pushing the two variable values onto the top of the stack. Two variable values onto the top of the stack. So pushing the data onto the top of the stack is nothing but what? Decrementing the SP by 1, SP by 1. So if you are decrementing the SP values right now, how much? 000DH. So you are decrementing the SP by 1 means, you are decrementing the SP by 1 means 000CH. D is nothing but what? It is a 15, it is a 14, it is a 13. 13 minus 1 means a 2. In hexadecimal format, it is going to be the C. So in this area, A variable is going to be stored. Means A is going to be, A is equals to the, here, A is going to be stored. Okay, I'll take the small letter. A is going to be stored. Okay, now. So means this variable is going to be stored. But you are expecting the two variables to get stored now. So means in the next, again, here for pushing the data, A variable, it is decremented by 1. To push the next B variable, again this SP content means, now the SP content is what? BP content is the starting address of the stack which is allocated for the main function. SP content is the how far you moved from the starting. So that is nothing but the SP content which is showing the top of the stack. Now as you are supposed to store the 16-bit B variable onto the top of the stack, SP is decremented by 1. Now the new values there in the SP is going to be, what is that? New values there in the SP is going to be the 000BH. Okay, and in this I am assuming that variable B is going to be stored. Variable B is going to be stored. Okay, now, but during in the main function, I just printed this one. We are simply printing the value, no problem at all. But in the main function, we are calling the subprogram. In the main function, we are calling the subprogram. When you are calling the subprogram, your execution control is diverting from here to here now. Actually, there are so many parameters which are going to be pushed onto the top of the stack when there is a execution diversion. Means actually execution should be done like this, but as we are calling the main for one subprogram, the execution control is transferred from one memory location to another memory location. When the execution control is diverted from one location to another location, after executing this function you should come back to this location now. So means you are supposed to remember the address from where exactly you left from the main function to the subprogram. So means all those addresses are also be going to push down to the top of the stack. But in order to avoid the conflict, what I am doing is I am simply assuming that address is already remembered by the microprocessor. Okay, now to avoid the confusion. So here in the main function, again what you are having? You are having the curly brace na open brace. Curly open brace means what? Asking the microprocessor to allocate a fresh stack area for the function 1 program. Okay, now. So when you are asking the microprocessor to hold the to assign a fresh stack area for the variables which are declared in the function 1, what you are supposed to do means you are supposed to, first of all, you are supposed to save the previous function starting address of the stack. Previous function starting address of the stack. What is the previous function starting address of the stack which is there in the BP? 000DH. Means this value should be pushed onto the top of the stack. So what is that value? 0, 0, and the next value is going to be the 0 T. Next value is going to be the, so what I'll do is I'll avoid this one. So here BP is nothing but the, it is going to be the, I'm going to take only the BP because that one is not good for explanation. I'll take the control B. Yeah. So assume that this is a BP register. That is a BP register, right? So from the main function, we are having the A variable. Take a small A variable is going to be stored, and the SP value is going to be the 000CH. Now small variable B is going to be there, and after that you are calling the subfunction and open brace. Open brace is nothing but allocating a fresh stack area for that particular program. So at that time, when you are trying to allocate a fresh stack area, you are supposed to remember from where exactly the stack area is going to be start for the function 1. So for that, what you are supposed to do, again you are supposed to use the BP register, base pointer register. But the base pointer register is holding the 000DH, which is showing the starting address of our stack allocated for the main function. Starting address of our stack allocated for the main function. So to remember the starting address of the stack allocated for the main function, what you are supposed to do, what the microprocessor is doing is, when you are diverting the execution control and starting the open brace. Starting the open brace is nothing but previous stack starting address is going to be pushed onto the top of the stack. Okay, now that is nothing but what is the previous address stack? 00000H 0DH. So this is a value. This is a value which was there in the, which is showing that this is a value which is showing the starting address of the stack for the main function. Okay, now, so after doing like this, what is the new value? The new memory location for the microprocessor. New memory location for the this particular stack. New memory location for this particular stack is going to be starts from the 00008H. Okay, now the BP value is going to be the, now the BP value is going to be the, BP value is going to be the 00008H, which is showing what? The starting address of the next stack allocated for the function 1. Okay, so means in this stack area, it is a BP value now. So in this BP value, X variable is going to be stored. X variable is going to be stored. Okay, so if you want to know in detail, it is going to be the BP. BP starting address is going to be 00008H, and in this location, it is holding the what? Is holding the, is holding what? X variable. Is holding the X variable, which is pointing the SP also, which is showing the stack pointer also. Okay, so the next case is in the function 1, we are calling the function 2 now. How many variables are there in the function 1? Only one variable, so only one memory location is allocated. Okay, now, but in the function 2, in the function 1, you are calling the function 2, means again the starting address of the stack allocated for the function 2 is going to be varying. So what was the previous value of the BP? 00008H now, that is pushed onto the top of the stack. 000 and 08 pushed onto the top of the stack. Pushed onto the top of the stack. Now, in the next memory location, 0005H is going to be the starting address for your function 2. Okay, now open brace is nothing but what? Just remember, in short, open brace is nothing but asking the microprocessor to allocate, or to remember from where exactly the, to show from where exactly the stack area is going to be starts for that particular function. Now, when you are terminating, so here we have done all these things now. Let me shorten this explanation. When you are executed the function 2, execution control is over now. You are returning from the function 2 to the function 1. You are returning from the function 2 to the function 1. Upon the close brace, whatever the area which is allocated. So here we allocated this area now. What was this value? This value was the y for the function 2. Whatever the area which is allocated for the function 2 on the stack, that is going to be vanished. Means y is going to be eliminated. Y is going to be eliminated, and this particular 0802 is there now. 0008 is there now, which is the starting address of the stack allocated for the function 2 now, storing the X value now. That is reloaded back into the PP. Means returning from here to here, means vanishing the allocated space in the stack for the function 2 is going to be vanishing. Means returning, close brace is nothing but closing the stack area allocated for the function 2 and returning to this one. Returning to this one means you should remember the starting address of your stack now. So means whatever the value which is pushed onto the top of the stack as a base pointer value, that value is reloaded back into the PP to point the starting address of the stack allocated for the function 1. Upon the execution of the close brace for the function 1, you are returning from here to the main function now. From here to the main function. At that time, what will happen? Again, the base pointer value for this particular main function is varying. For this one is separate, for this one is separate, for this one is separate. As you are returning from here to here, then whatever the area which is allocated for the function 1 is also going to be vanished. And for the main function, what is the starting address? 000DH na? That is reloaded back into the BP register. That is reloaded back into the BP register. Reloaded back into the BP register. Okay, means 000DH is going to be reloaded. Reloaded means again it is pointing the this area. This area belongs to what? This is a stack area allocated for the main function. This is a stack area allocated for the main function. Okay. So in short, open brace is nothing but, open brace is nothing but, it is going to be, means it is loading the some address as a starting address of the stack to that particular function into the BP register. BP register is showing the a particular function stack from where exactly it is going to be started in the stack segment. SP is indicating the how far, how many memory locations are going to be utilized in that particular function. That is the SP. What is the starting address of the stack for that particular function indicated with the BP? What is the starting address? What is the last memory location which is allocated for, which is accessed for that particular function is going to be shown by the SP. Starting one is the BP. Last memory location is the SP. Okay. When you are moving from here, when you are moving from this particular one to this particular one, moving back to the function called function. So f1 is f2, function 2 is nothing but the calling function. Yeah, the whatever the function which is called. So you are moving back to moving back from function 1 to the function, sorry, function 2 to the function 1. At that time, without knowing to you, you are vanishing the space, or you are eliminating the space allocated for stack space which is allocated for the function 2. So that is going to be done by the micro compiler, C compiler, by watching the close brace. Okay. So here, by watching the close brace, when you are moving from the function 1 to the called function, moving back from the function 1 to the function 2, you are using the close brace. Now close brace means vanish the space allocated for stack space allocated for this function. Okay. So open brace is nothing but from where it is used for, from where exactly the stack is going to be starts for that particular function. That may be the main function or sub function. Close brace is nothing but termination or vanishing the memory allocated, vanishing the stack memory which is allocated for that particular function. Okay. So declaration of the variables in C language is nothing but, declaration of the variables in C language is nothing but asking the microprocessor to assign some memory locations, on the top of the stack, Okay. So that is the usage of our open brace and close brace. Okay. So this is all about our stack. Means stack is nothing but, the microprocessor is always using the stack area when it is trying to execute the program. Means when it is executing the main program, it is using the stack. Stack main function is to hold the variables which are declared in that particular program, in the function body. Okay. So this is all about our stack and the C programming part. If you are having any doubts regarding this, so let me know that one in the WhatsApp group questioning format. So one of the girl answered that question, which is nothing but in order to sustain the variables, we are having the open brace and the close brace. That's good, but what exactly happening means the BP register is filled with the starting address of the stack allocated for that particular program. SP register is going to be points the top of the stack in that stack region which is allocated for a particular program. Okay. Now, what about the SS? Okay. Now, what about the SS? Let me tell you this one. Okay. Now, yeah, let me tell this point. One of the important point. Control T, Control 2. So in order to access the SS stack segment, we are having the stack segment base address. In order to generate the 20-bit physical address, we require the base address as well as the offset address. Base address of the stack is there in the SS register, stack segment register, and offset address is there in which register? BP or SP. When it is going to be used the BP in order to show the starting address of the stack allocated to a particular memory, particular program, and when it is going to be used the SP in order to show that how far it is moved from the starting of that particular stack to a particular program, that is going to be indicated by the SP. Okay. So SP, BP both are showing the offset address, but if you are not considering the SS, if you are keeping the SS aside, then BP is showing the starting address of the stack allocated for a particular program. SP is showing that last memory location for the in that particular stack in that particular program, for a particular program. Okay. So this is the BP and the SP. BP means base pointer, which is showing the starting of the stack for a particular program. SP is nothing but the top of the stack, which is showing the last memory location in that particular stack allocated for a particular program. And SS showing the entire segment base address. Okay. So I think that's why we are having the BP slash SP, means two offset addresses are there. One offset address is always showing the starting address of a stack for a particular program. For every program, we are having the starting address of the stack. So that is going to be indicated in the indicated by the BP content, which is the base pointer register, and SP pointer, that is the stack pointer, is indicating the what is that? Stack pointer register is indicating the top of the stack in that particular stack region, which is allocated for a particular program. That may be the main function or function 1 or the function 2. Okay. So this is all about our stack area in 8086 microprocessor. Not only the 8086, everywhere, wherever you are using the microprocessor, this is the operation which is going to be done by the system. Okay. So, but in case of the microcontroller, stack operations are going to be reversed. Okay, now I'm not considering that particular microcontroller concept, but in case of the microprocessor, any microprocessor based system, this is the thing which is happening inside the system. Okay, that's all for today's class. We'll continue in the next class. Thank you. Oops, I'm sorry. I'm sorry. Let me come back. Uh, I thought it is not there, so it is going to be, yeah. SP is nothing but, I'm sorry. SP is holding the, come on, man. I thought transition was there. It is not that. So for SS stack segment, we are having the two registers. One is a BP slash SP. I'm sorry. I thought that it is recording, but it was not. Okay. So SP and BP. So SP is holding the SS is holding the stack segment base address of the segment, which is allocated as, which is treated as a stack, and BP is holding the starting address of the stack allocated for a particular program. SP is showing the top of the stack in that particular stack area allocated for a particular program. Okay. So BP is showing the starting address of the stack for a particular program. SP is showing the top of the stack in that particular program, and SS is showing the starting address of the entire segment. Okay. So this is all about our BPSP concept and the stack explanation in any microprocessor based system. I'm sorry, I thought that it was recording, but when I come back to here, I came to know that it is not recording. Okay, so that's all for today's class. So if you are having any queries regarding the stack, let me know in the queue. Okay, thank you.